Now let's talk about normal versus non-normal cash flows. Normal cash flow project refers to the project with cost, followed by a series of positive cash flows. So there is only one change of signs. You started with negative cash flow, and then next year it becomes positive, or say cash inflow, and thereafter. Only one change of sign from negative to positive. Non-normal cash flow projects refer to the project with two or more changes of signs. So for example, nuclear power plant or strip mine, they have cost, which is negative cash flow at time 0, and then string of positive cash flows from the operation, and then the cost, which is negative again to close the project. Why do we have to differentiate between projects with normal cash flows and projects with non-normal cash flows? The example on the next two slides explains why. If we have a non-normal project as shown on the following timeline, as you see, the sign changes from negative 800 to a positive 5,000, but then from 5,000 to a negative 5,000, so the sign changed twice. This is a typical project with non-normal cash flows. Now, if we enter these cash flows into the financial calculator, and we enter a discount rate of 10%, we can get the NPV of a negative 386.78, which suggests this project is not acceptable. What about its IRR? Remember we mentioned that IRR is the discount rate that makes your NPV 0, or say it's where your NPV curve meets the x-axis, or say the horizontal line in the NPV profile graph. However, in this case, if we try to map the NPV of this project, this non-normal project, and we notice that when we have a 25% WACC, NPV is 0. And then when we have a 400% WACC, NPV will also be 0. So we have this project that has two IRRs, and under each IRR, NPV is 0. So the NPV actually goes up as the WACC gets higher, and then after this point, the NPV starts to go down, and so the whole curve meets the x-axis twice. To understand this, we realize that at very low discount rates, the present value of the second year's cash flow is large and negative, so NPV is lower than 0. And then at very high discount rate, the present value of both year 1 cash flow and year 2 cash flow are low, so the initial investment CF0 dominates, and again NPV is lower than 0. In between, the discount rate hits the second year cash flow harder than the first year cash flow, so you do have positive NPV. So the result is we do have two IRRs. The existence of two IRRs make the capital budgeting decision a little bit harder. So we can try to calculate the modified IRR. In this case, because we do have two outflows, we'll calculate the total present value of both outflows, and the present value of the first one is simply a negative $800,000 itself, and the present value of this one will be the negative 5 million divided by 1 plus 10% at the power of 2. You add up those two numbers, and the total is a negative 4.9 million. The future value, or say the terminal value of the cash inflow 5 million, we'll calculate the future value of it at the end of year 2, or say 1 year later. Remember, for MIRR calculation, we assume these cash inflows are reinvested at the WACC. So with the WACC as a rate of return, we calculate the future value. It turns out to be 5.5 million. Then, what kind of return makes your 4.9 million plus investment become 5.5 million in 2 years? It turns out to be 5.6%. 5.6% is actually lower than the WACC of 10%, so we should reject the project. This is consistent with the decision we make based on the NPV criteria. Remember, NPV is negative, so we also want to reject the project based on the negative NPV. The last capital budgeting technique we want to talk about is the probability index. The probability index, or PI, is the present value of future cash flows divided by the initial cost. So it measures the bang for the buck. I'll say for $1 of investment, what is the present value of future cash flows? And in this example, when we look at project L, we calculate the total present value of all its future cash flows, add up, and then divided by the initial cost of $100. So PI is 1.1879. If we want to calculate the probability index for project S as a practice, go ahead and you should have a result that is 1.1998. As you see, probability index and NPV are very similar. NPV is the total present value of future cash flows minus the initial cost, while PI is the total present value of future cash flows divided by the initial cost. So their conclusions can be very consistent. When you have a positive NPV project, its probability index will be greater than 1. When you have a negative NPV project, its probability index will be lower than 1. Now, let's look at the capital budgeting decision under some special situations. We'll first talk about projects with unequal lives. In the following example, you have project S, a shorter project, and project L, a longer project, that they are mutually exclusive. And we have 10% back for both projects. And you see that project S takes 2 years and project L takes 4 years. By now, you should be able to calculate the NPV for both projects pretty easily, under 10% back. The result shows that for project S, NPV is 4,132 and NPV of project L is 6,190. So apparently, NPV of project L is greater than the NPV of project S. But can we say L is truly better? Don't forget, project L takes 4 years and project S takes only 2 years. So we want to compare these two projects on a common basis. And to do that, we can use a so-called replacement chain approach. So notice here that the project takes only 2 years and can be repeated after 2 years to generate additional cash flows or additional profits. Under this replacement chain approach, we repeat project S so that we are looking at a 4-year period. The result is shown on the next slides. Here we are replicating project S after 2 years. So this is exactly the same as the original project. We just try to do it one more time for another 2 years. So initial investment of 100 and first year cash flow 60, second year cash flow 60. If we look at the whole 4 years, initial investment at time 0 is 100 and first year we get 60. But then for the second year, because we have to make another investment of 100, then the total is a negative 40. And then we have year 3 and year 4 cash flows from doing this project one more time. So 60 for year 3 and 60 for year 4. Then we look at this timeline and we calculate NPV based on 10% back. And now NPV for this is 7,547. And this is greater than the NPV of project L, which is 6,190. So in that case, project S seems to be more desirable. Now, if we have to consider more variables in this replacement chain approach, for example, suppose the cost to repeat S in 2 years had to rise to 105 instead of the same 100 as before. Then the conclusion may be a little bit different after we calculate the NPV. So if we replicate the project by the end of year 2 with an initial investment of 105 instead of just 100, and cash inflows are the same. So as you see, second year the net cash flow is a negative 45. And so we try to calculate the net present value of this 4-year project with your initial investment of negative 100, first year cash flow 60, second year cash flow of negative 45, and third year and fourth year cash flow of 60 for each year. Then we calculate NPV, and it turns out the NPV is 3,415 based on 10% back, and this is lower than the 6,190 for project L. And in this case, if it gets more expensive to repeat project S later, then we should choose project L based on the NPV comparison for both 4-year projects. So as you see, what we did here is to replicate project S so that we are looking at a 4-year project which is consistent with project L, and this way we are comparing apple to apple instead of a very short-term project versus a very long-term project. Now let's take a look at so-called economic life of a project. Consider another project with a 3-year life. The cash flows are described in the following table. For example, if you decide to terminate the project by year 1, you can sell the machines. The project itself generates 2100 cash flow in year 1. And by selling the machines, you receive another 3100. But if you terminate the project after 3 years, you receive 3 years cash flows from the project, but then there's no salvage value left from selling the machine. So the question is, should you always operate for the full physical life of 3 years, or should you terminate the project before you use the machine or the equipment for their full physical lives? To answer that question, we can analyze the cash flows for all 3 different scenarios. So scenario 1 is there's no termination. We try to use the equipment for all 3 years. Second scenario is we terminate after 2 years. So in that case, year 1 we receive cash flow from the project, and year 2 we receive some cash flows from the project, and we receive some money from selling the equipment, and the total amount of cash is 4 million. And if we terminate after just 1 year, then we receive some cash flows from the project, and we also receive some money from selling the equipment by the end of year 1. The total is 5.2. Now we can calculate the NPV under each scenario, assume a 10% cost of capital. If we want to use the equipment for full 3 years, the NPV turns out to be a negative 123. But if we can sell the equipment by the end of year 2 and get some money out of selling the equipment, the NPV actually is a positive 215. If we terminate just after 1 year, we get some money from selling the machine, but we're not getting enough from operating the project, so the NPV is also negative. And that means the project is only acceptable if we operate it for 2 years and then sell the equipment by the end of year 2. The conclusion here is a project's engineering life, which is 3 years in this example, does not always equal to its economic life. So economic life is the number of years that we achieve the highest NPV if we consider both the cash flows from the project and the cash flows from liquidating or say selling the equipment. To summarize this whole lecture, in this lesson we review the concepts and calculations of several basic capital budgeting techniques, including the payback, NPV, IRR and modified IRR, and profitability index. We also discussed the limitation of some capital budgeting techniques. For example, payback period ignores time value of money and cash flows after the payback. Non-normal projects may have multiple IRR results, which make the capital budgeting decision a little bit hard to make. We introduced the replacement chain approach to apply the capital budgeting tool in analyzing and comparing projects with unequal lives. Project's economic life may not necessarily equal to its physical life, and we can apply the capital budgeting tool to analyze the best economical life for a project. In the next lesson, we'll focus on how to estimate the cash flows for a potential project so that we can apply the techniques introduced in this lecture and perform a reasonable capital budgeting analysis. The next few slides for this lecture are about the discussion questions related to the capital budgeting techniques. So as usual, the discussion questions and case assignments are not included in the video, but again, I would recommend you to take a look at the guideline before you try your discussion assignments. And if you have any questions, feel free to contact me or feel free to post on your D2L discussion board